This first past paper question you'll see is very familiar to us. In a certain computer, real numbers are stored in floating point form using 16 bits. 10 bits are given aside to the mantissa, that's in 2's complement, and the exponent is 6 bits again in 2's complement. So for part 4a, convert the number 5.75 into this floating point form. Your final answer should be normalized. So, how does the mark scheme break this down? Because this is AS content essentially, isn't it? Well, you get 1 mark for obtaining the binary fraction. So we're looking for 101.11 is all we need to represent 5.75. Of course, to normalize it then, we need to put it in 2's complement, so we'd add an extra 0 at the beginning because the negative value is turned off. Then we need to work out how far the exponent needs to represent. So the exponent needs to represent 3. So using all that bit pattern, we've got 0, 0, 0, 0, 1, 1. And the mantissa then, we just copy down the values as they appear and fill the remaining gaps with zeros. 0, 1, 0, 1, 1, 1, 0, 0, 0, 0. Reasonably straightforward and using that exact same method that I showed you earlier. Part B, 2 different numbers are to be multiplied. 3 different methods are considered. Method 1 is round them to integers, then multiply. Method 2, multiply the decimal numbers, then round. Method 3, multiply the decimal numbers, then truncate. Now this is a massive marks question, 6 marks for this. Calculate the absolute errors that would occur from each of these methods in comparison to the full accuracy of the decimal calculation. Okay, so what we need to do here is start by doing that calculation. 25.5 times 5.75 gives us 146.625. So that's the completely accurate answer that we want to get to. So let's look at doing this. With method 1, where we round and then multiply, what we're looking at is we're looking at multiplying 26 by 6. That gives us 156. So the error from the accurate answer is 9.375. Let's work through method 2. That's multiply, then round. So that is 25.5 times 5.75 and then round it. So we're rounding 106.625. The nearest whole number is 147. So the error there is only 0.375. Truncation then is multiply and then truncate. So we've got the answer 146.625 and our error there is 0.625. So you can see there that the method chosen increases or decreases the accuracy at different points, and you remember that rounding is more costly in terms of processing time than truncating is. So although the third error there has a significant margin of error, it is probably quicker to compute that than elsewhere. Part 2 to section B is to discuss the relative accuracies of each of these 3 methods. So let's go through them one at a time and have a think about why each method is good or bad. Well, first of all, we want to just say which are the most accurate. There are 3 marks just identifying out of those results which one's the most accurate. So we're going to say, right, method 2 is the most accurate because the absolute error is the smallest. Method 1 is the least accurate because the absolute error is the largest. And method 3 is somewhere in the middle, but it's neither the most nor least accurate. We then need to mention rounding. Why is rounding always as good as truncating and often better? Well, the reason for that is, although rounding is computationally more complex, we always find the closest value. So the accuracy is always the smallest it can possibly be with rounding. With truncating, if I need to round up, a truncation would take it down. That would increase the gap then in the accuracy. The final mark on this question is for saying that the greatest overall accuracy is achieved by completing all stages of a calculation to a maximum available decimal places with only rounding or truncating at the end. And that's because we don't end up with a result that is calculated from 2 rounded values. The larger the multiplication, the more that rounding error has an impact. So you always want to do as much of the multiplication and as much of the maths as possible in the maximum of decimal places and only round it at the end when we need to show it or describe it to somebody else. Part C, integers are stored in a different computer system in 16 bits using 2's complementation. demonstrate your working how the computer would store the value -152 in decimal. So the first thing we want is to show that being represented in positive. So that is just representing that with 16 bits, reasonably straightforward. And then for 2's complement, you'd need to turn on the most significant bit. Now this is where my preferred method is a bit of a faff, because you would need to manually work out all of that. Now the bit flipping, what you do for that is you work from the right hand side, you leave everything the same up until you get to the first 1. And from that point onwards, as you move to the left, every bit is flipped, every bit is the opposite. And we end up with this easy 2 marks for a reasonably complex calculation using my method. So bit flipping has its purpose, I suppose. Another past paper question here where the question is broken down into 6 and 7. 6a, explain, giving an example how an integer can be subtracted from another integer using 2's complementation. Okay, well again, this is reasonably straightforward. The way this is actually done is with addition. So you add them together, you've got a mark for generating the correct negative number out of the addition and a mark for making sure that the addition is actually correct within that sum. And it's reasonably straightforward to do that. Part B, identify 3 types of error that could occur when performing logical left shifts on a number in 2's complement form. Well, first of all, we've got overflow. It could go above the maximum bit capacity of the register. We could end up with a negative number becoming positive if we overflow the sign bit only. And the same thing with the positive to negative. If the sign bit is overflowed, then we lose that information about whether it is a negative or positive number. Underflow is where all the 1s disappear and we're left with 0 if we were to go the opposite way. Question 7 then, in a certain computer system, real numbers are stored in floating point form using 2's complementation, a 10-bit mantissa and a 6-bit exponent this time. And you'll see the question is written in a slightly different way. Calculate the denary number, my favorite word, denary not decimal, represented by the floating point number. So we've got our mantissa on the left, our exponent on the right. What we have to do is work out what the exponent is telling us to do, then move the decimal point. And the decimal point is implicitly after the first value. So it's 0.1101101000. What it's telling us to do is move the exponent in a positive direction 7 spaces. So that's 7 spaces to the right. So what that does is it ends up giving us a denary answer of 109 once you work all those things out. Part B, state the effect in the result on question 7a if 1 is subtracted from the value of the exponent to give us 000110 and work out with the denary number. And this is reasonably straightforward because it's going to actually half the result. Now let's think about why that's the case. Well, what we're saying this time is instead of moving it 7 places, we're going to move it 6 places. And if you remember that has the effect of dividing it by 2, so halving the result. So if you knew that, that's a reasonably easy question to calculate the result on. C part 1 then, calculate the effect of carrying out an arithmetic shift left by 2 places on the 8-bit positive integer 00001111 and state the effect of this operation on the numbers. It's 2 marked, it's reasonably easy. You end up with 00111100 because we've moved to the left by 2 places and an arithmetic shift fills the blanks with zeros. What that has the impact of doing is multiplying by 4. Every time we shift a space, we multiply by 2. So it's 2 times 2, which is times 4. Now you can't say gets bigger, you can't say moves 2 places to the left, because what the question is really about is what does that do to the value? The question is not really about what is the practical method that you're getting involved in. It is what does it do to the numbers? You need to be specific in a mathematical way. 7c part 2. If an arithmetic shift left by 2 places was carried out on the 8-bit positive integer 01001111, a problem would arise. Name and describe the problem. You can probably see that if we take those leftmost 2 bits, they would vanish, they would be overflowed. So we'd say there's a numeric overflow, so we would lose that 1, they'd disappear. And so because the resulting number is too large to be contained in the 8 bits available, we lose accuracy and we lose the correct answer. I'd hope you'd agree that the past paper questions aren't exactly a revelation. They're not new and exciting, but they are asking you with a bit more rigor to do the same things you did for AS and apply those to the new methods we talked about for A2.